Hi, and my name is Alvarado Rodriguez. I'm a fourth-year PhD student at New Jersey Institute of Technology, where I have been working at the intersection of creating software for high-performance computing and graph theory. I'm here today to present this talk on the design of graph analytical software in Chapel. Oop. Okay, my slides finally advanced. So to start off, when we talk about developing graph analytical software, we often look at two main problems, which include the design of efficient graph data structures that can handle fast data accesses and algorithms that can exploit these fast data accesses. To these ends, we have implemented variations of highly parallel and distributable edge-based graph data structures based on a modified version of CSR that we have come to name the double index structure, or DI for short, due to its ability to quickly query the graph on vertex and edge indices. Further, we have optimized algorithms around this DI structure, including, but not only breadth first search, triangle counting, and connected components. All of our functionality is bundled into the framework that we have come to call Arachne, which is built on top of our CUDA. Firstly, in this talk, I will do a brief overview of DI with a focus on how we have enabled the structure to store properties on both the vertices and edges of graphs. Then I will share a journey of optimizing breadth first search for distributed and memory extension in Chapel. So Arachne is built as an extension to our CUDA on top of our CUDA. At the top, we see a typical workflow that consists of creating a graph from some data that is loaded into our CUDA arrays that allows for local storage of properties with the vertices and edges of the graph. This can then be analyzed by a suite of graph algorithms or quickly queried to generate smaller subgraphs for continued analysis and other graph tools. The user connects to a server through a Python script or a Jupyter instance and loads in Arachne just as they would load in our CUDA. And they can use both of them together in one interactive session. Our backend looks similar to our CUDAs, where our modules are built to accept operations from Python, area functionality, and then return successes and the end result back to the user. We directly persist all our graph data in the CUDA symbol table by using their server data storage framework. Our work is open source and can be seen by following the link I have shown here. And we have done publications, presentations, and tutorials at conferences like HVEC, IPC, IPDPS, and PPOP, and previously last year's ChapelCon, which was Chewy, and the year before that too. So here I just provide a quick modular overview of Arachne functionality. Where in green on the left, we have the functions that consist of converting data into our graph format or to randomly generate graphs. Then once the format is in our DI data structure, we can then execute a suite of graph algorithms and query the graph to return results as either more PD arrays, as a new graph, or some type of integer or real value. The backbone of our algorithms and Arachne itself is our DI data structure. So now we will show some examples and a brief overview of the objects that allow us to persist this data in the CUDA symbol table. Here we show the arrays that make up our graph information. That this example here is built directly from the sample graph on the right. The edges are stored in the SRC or DST arrays, which are sorted, given some vertex u. In this case, if u is 0, it's adjacency list in constant time, but by performing a slicing operation on both source and destination arrays. Say you're given an edge index e, You can find all the vertices and make up this edge in constant time by avoiding a binary search, unlike in CSR. If you want the edges with the vertex names from the original graph, you simply just need to run an indexing operation on source or destination with the map array on the left here. Lastly, say you're using two locales for execution. Our data structure just uses the default block distribution to split up the arrays of the data structure, in this case onto locale 1 and locale 2. I need some water. When enhancing the vertices and edges of a graph with properties, we also store these in block distributed arrays as well to ensure that all the data is stored locally with a given vertex or edge. For example, given some vertex or edge index, a developer can loop over the names of the arrays in the symbol table, extract them as a reference, and then extract the given information for the index value that they are searching for. If the index does not exist in the sparse array itself, then it would just return the n and z value of the sparse array. We persist our graph data via some classes I inherit from both composite symmetry and gin symmetry, which are classes in Arcuda. The two most important ones are graph symmetry, that allows us to actually store our graph objects, and sparse symmetry, that allows us to store our sparse property arrays in the symbol table. We also have some other special objects to store maps, replicated arrays, associative ones, and other objects that are needed either for the DI data structure itself or for different algorithms. We are currently also working on generating sparse versions of our CUDA string objects and categoricals. Now we move on to onto our journey, I guess my journey of optimizing breadth first search for multi-locale mode. So some general information about breadth first search itself. It's an important algorithm for answering problems like how far is one vertex from some given source. It is a fundamental graph algorithm that everyone learns in an introductory class to algorithms in computer science. It is known to have a sequential complexity of big O of n plus m, where n is the number of vertices and m is the number of edges. And when we look at a parallelized version of breadth first search, it consists of looping over a current frontier and generating the next frontier from the previous frontier. Given some source vertex, in this case, it's the green one here, 0. We first visit its one hop adjacency list, and we add them into the next frontier. Move to the current frontier, where their neighbors are expanded independently from each other. So once this loads, we can expand the adjacency list of 5, 7, and 2 without needing any information between 5 and 7 or 7 and 2. Once we have visited all of the vertices of the graph, then we return an array where every index corresponds to a vertex of our graph, and every item stored is how far that vertex is from the source. When we explore breadth first search in a multi-locale environment, we run into some extra difficulties. We're generating a frontier, might involve having to transfer information from one locale to a remote one. In this example, the edges highlighted in green consist of a communication that has to happen between the different locales in our environment. In this case, expanding the neighborhood of 0 consists of having to transfer the communication to the blue locale to say, hey, for the next iteration of breadth first search, we're going to expand the adjacency list of 5 and 7 on locale blue. Then we can also use aggregators to ensure we aren't making too many fine-grained rates which usually reflects speedups in execution. For example, at the first iteration, when expanding the adjacency list of 0, we could aggregate 5 and 7 on a buffer on locale red, and then transmit that information to the blue locale, and store that information in its frontier list. Here we see that the edges between first search iterations can cause and multiple copies of the same vertex to be transferred to the next frontier list. So now I'm going to show some code. I hope it's big enough for everyone to see. I apologize for the size. I was trying to fit a lot on a small slide. This particular version of breadth first search is version 1.0, which corresponds to the diagram here, where we tried to make code that ran well on one locale, kind of just distributed kind of in a naively way while trying to still take care of some locality. It uses the idea of forward edges and reverse edges for undirected graphs. We're given an edge UV, you store 2 copies of it for an undirected graph. You store U in source and V in destination. And then you also have the reverse storage, where you store V in source R and U in destination R. For this code and these experiments, we use the old version of this distributed bag to hold the frontiers pre-Chapel 2.0. So the results reflected here are for that old version of the bag. You can see here highlighted in yellow, where we expand the frontiers based on the 4 edges of the graph. And then in red, we expand the frontier based on the reverse edges of the graph. We can also see here that that we're kind of doing the same work 2 times. And this for all loop probably spawned some tasks on the locale where item I lived for set coref, which means that there could have been some remote communications if the variables here did not live on the locale that is processing that item from the current frontier. And we're doing that twice. So you could see that if we're doing double the work, if we removed the red part and symmetrized our edge list, then maybe we would see some improvements. So we did just that. We remove all the code after that. We symmetrize our edge list, which means that every vertex automatically will have access to all the vertices in its adjacency list. And then the version after that, after a lot of thinking, we said, what happens if we use aggregators to transfer the information to a frontier that is maintained on each locale in the environment. So as you can see there, we end up with some much nicer, cleaner looking code compared to our previous attempts. And then we can see here that we have both and parallelism across the locales and also within each of them. We use an aggregator here per task. We make sure that we are maintaining locality where we're expanding our adjacency lists here. And then we expand the adjacency list of each vertex. And then we do the transfer of the neighbors of that vertex using this frontier ag.copy right here. And then this heat map shows that from version 1.0 to 1.5 to 2.0, we had a quick reduction of the number of communications that happened in the program. And then we went from it taking 84 seconds in version 1.0 to it taking 3.36 seconds in version 2.0. And this experimentation was on 8 locales. And then I also have some slight scalability results for breadth first search. As the number of locales goes from 2 to 64. You can see here that for our sample graphs here, which are randomly generated RMAC graphs, we see a reduction in the execution time. as the number of locales increase. So some lessons learned. Using Chapel or any PGAS-based framework doesn't magically get rid of the complication of parallelizing and distributing graph operations, since they are usually very highly irregular. Adapting communication network optimizations, such as being aware of how the neighborhoods are split across the locales in your environment, can definitely help improve graph-based performances. In conclusion, using a programming language like Chapel allows us to implement both shared memory and distributed algorithms to enable a highly productive large-scale graph analysis. And using an existing framework like Arcuda allows us to focus more on the graph algorithms while offloading tasks such as object persistence and array sorting to Arcuda, so we don't have to worry about it. So some future work we have planned includes things like allowing bulk jobs to use Chapel's ability of hybrid execution a lot better. Instead of one massive graph, you may have a massive amount of small graphs where we can store all of them on different compute nodes and then run one locale parallel algorithm for a subset of graphs on each of the locales. Maybe sometimes you just want to call out to other frameworks in C++ with MPI or YGM. We just have to figure out how to properly handle that data transference. I think I'm running out of time. Maybe we can do some more dynamic optimizations where we can specify the number of threads that we want a loop to use instead. And last but not least, there isn't one structure to rule them all. Maybe we want ways to recreate or transfer the data from different types of graph formats, where one might be specifically more better for an algorithm. For example, our edge-based structure is very good for connected components, but probably isn't the best choice for breadth first search. That could probably see improvements from using a more vertex-centric data structure. Yeah, that's it. Thank you. I can take any questions now.
Thank you so much, Oliver. That was interesting multi-locale work. I really enjoyed that. So yeah, already we have some questions. So Trent, yeah, please go ahead and unmute yourself.
Sure. Yeah, I was just curious if you have any support for hypergraphs where an edge would have two or more vertices.
So in Arachne, we currently don't have support for that, but there is a Chapel hypergraph library available. I don't know the last time that got updated, but its code is on GitHub somewhere.
Okay.
Yeah.
Cool. Thanks.
No problem.
Any other questions? I was just wondering, you implemented on multi-locale, right? And you were transferring data between so the transferring data or information or communication was from one locale with all others, or for example, one locale had communication with all 7 locales?
Yeah, so I guess that depends on the adjacency list you're currently expanding. There might have been a case where I was transferring to all the other ones as well, but for each iteration of the for all loop, it should be one locale transmitting up to at least all the other ones.
I see.
Yeah.
No deadlocks?
I don't think so.
Okay,
Maybe. Yeah.
Perfect. So thank you so much, Oliver, for the great presentation.